Well, welcome back, statistics scholars. Our last two topics to prepare you for the first exam are actually going to be our first foray into actual calculation. We are going to be calculating statistics today. We're going to be calculating measures of central tendency, and we're going to be calculating measures of variability. Now, one of the measures of central tendency I'm absolutely certain you've heard of before, and that is the average. Like when students ask me what was the average in the class, they're actually referring to a measure of central tendency. And we're going to go over three of them. We're going to go over the arithmetic mean, also known as the average, add up a bunch of things, divide by those number of things, right? Add up all the scores in class, divide by the total of people in class, you have the average. It's the arithmetic mean. We're also going to go over the median, and we're also going to go over the mode. And what I have here on the very first slide is sort of a visual representation of the mean, median, and mode. Let's say this is the number. Let's say this is a big company down in LA, and this is how much people make per month. We have a group of people, sort of the most frequently occurring group of people is the people who make $2,000 a month, right? That would be the mode because it's the most frequently occurring score. Then we have the median, and that's the score, right? So $2,000 a month is the mode. It's the most frequent score. Then you have the median, and that's the score that is directly in the center of the scores, meaning quite literally there's the exact same scores above it as there are scores below it. And if you count, you'll see that there are 12 above this person's monthly income and 12 below. And so the score of 3,000 becomes the median because it's directly in the center of the scores. The same actual number of scores is above and below it. But then you have the arithmetic mean or the arithmetical average. Those are just synonyms for the same idea. And that's going to be the score that's going to be in the center of the values. Not necessarily the same number of people above and below it, but rather it's going to mathematically find the score that has the same amount of stuff, so in this case, monthly income, the same amount of stuff above and below that score. So in this case, 5,700 is the average monthly income because there is somebody with a really, really high monthly income, like the CEO of this company, $45,000 a month, and then a couple people, three people who also make an absurd amount of money, $15,000 a month and $10,000 a month, and those numbers are pulling the average towards themselves, sort of like in a class, if everyone, let's say, gets a 70 out of 100, and then there's like three people who get 100 out of 100, those people who ace the exam are going to sort of throw off the average. They're going to pull the average towards themselves. So that's the idea. And so these measures of central tendency are three different ways of answering the question, who is typical? Who is a typical person? You can define that as the most frequently occurring person. You can define that as the person in the dead center, the same number of people above and below, or you can define that as the score where the same amount of stuff is above and below, where the amount of income in this example is above 5,700 as below 5,700. And that's what it means to talk about a measure of central tendency. Who is typical? But before we go deeper into measures of central tendency, because we're going to dive deeply into both the mean, median, and the mode, call them the three M's, I first want to make clear what we're going over today. We are going to be calculating our very first statistics, but these are descriptive statistics. Now, to refresh your memory, a statistic is any number that you calculate for a sample. Now, they're used to make estimates about or make decisions about populations. Always. In research, we are always trying to make estimates about or make decisions about populations, that big group of people that we care about when we ask and answer a research question. And a statistic is a number that you calculate for a sample that you then use and apply to a population. And what we're going to be calculating today are our descriptive statistics, our measures of central tendency, mean, median, and mode, and our measures of variability, which we'll go over in a little while, which are standard deviation, quartiles, mid-spread, range, and variance. And we're not going to go over all the different descriptive statistics that exist, right? There are lots. In fact, there are more measures of central tendency than the mean, median, and mode. And we're not going to cover those other measures. But I just want you to understand at this point, when we calculate the mean, median, and mode, and when we calculate these numbers that represent variability, more on that in a little bit, we're calculating statistics that simply describe what the population might be like, right? They're just describing like who is typical, or which is the measures of central tendency, or how spread out are the people compared to one another. Are people super close together, or are people super far apart? So descriptive statistics describe one variable. They describe the nature of a single variable. What is a typical value on that variable? Mean, median, and mode. How spread out are the scores on that variable? Are the scores super tightly packed together, or are the scores super spread out? That is variability. But you're describing what the population might be like by calculating descriptive statistics for a single variable. What is this single variable like in a very descriptive way? Again, you're still trying to make estimates about a population, but this is like your first step. Just tell me what this single variable is like. Let's say we're doing the number of children, right? The number of children is a quantitative variable. Higher numbers mean more children than lower numbers, to refresh your memory. And I could calculate the average number of children in the United States. And let's say I calculated it for a sample of 1,000 people. Assume perfectly randomly selected random sample of 1,000 families. And I say, okay, how many children do you have? And then I could calculate that average, the average number of children for those 1,000 people in my sample. That would be an example of a descriptive statistic because it allows me to make an estimate about the average for one variable in the population. The same thing when we learn to calculate measures of variability, which is asking a different question. It's not asking who is typical, but rather we're asking how spread out are people. And for something like the number of children that you have, it's not people are not actually particularly spread out. Most people are pretty packed. The average number of children in the United States is just under 2 when you look at sort of the average. But most people are not super spread out. It's not like there are people with negative 70 children. In fact, you can't have negative children, right? You're sort of, there's a hard wall at 0. You have 0 children. But you know, and most people have 2 or 1. There are not very many people who have 4, 5, 6, 7, 8, 9, 10. So most people are packed pretty close together. Not a whole lot of variability. That is what variability gets at. And it's a number that you can calculate. Just like you can calculate an average, we can calculate measures of variability. But again, they simply allow us to describe the nature of a single variable, who is typical and how spread out it is, are the only two sort of descriptive statistics we're going to wrap our head around. This is different than inferential statistics. Now, if you recall from our discussion of data, we talked about research questions and how all statistics and data analysis is really trying to address research questions. And the kind of research questions that I sort of shared with you, almost always involved more than one variable. Is age related to cognitive functioning? Is gender, men versus women, related to aggression? These are much more nuanced, much more interesting questions. And in order to answer these questions, we're going to have to first calculate some descriptive statistics, but then we're going to have to go beyond that and calculate what are called inferential statistics, which allows us to make an inference, which is a fancy word for decision, allow us to make a decision about a research question that involves more than one variable. Right? So we're going to calculate z-tests, t-tests, f-tests, and chi-square tests. That's that X-looking thing down there, right here. That's actually a chi-square. It's a Greek letter. It's an uppercase Greek letter. And essentially, these tests, z, t, f, etc., generate z, t, f, and chi-square statistics. But these are going to be second step statistics. They go beyond averages. They go beyond descriptive statistics to allow us to answer much more interesting, complex research questions. And so a z-test creates a z-statistic. A t-test creates a t-statistic. They'll allow us to ask and answer research questions. And we're not going to get to that for weeks. But I wanted to just broach for you now. I wanted to introduce the idea that there's two sort of family of statistics. They're the basic statistics that are just descriptive, simply allow us, using our samples, to describe what a single one variable is like in the population. What's the average number of children? What is the variability in income? These are examples of statistics you could calculate for a sample that would allow you to make an estimate for a population on that single variable. And our next step, after we've learned all about descriptive statistics, eventually we'll get to what are called inferential statistics that allow us to ask and answer those very cool research questions I shared with you when we talked about data. And so our first category of descriptive statistics we're going to go over are going to be measures of central tendency, which asks the question, what is a typical score on this single variable? If I was going to grab a score from this single quantitative variable, because central tendency, measures of central tendency are most often applied to quantitative data. And in fact, I should just mention now, we're going to be sitting with quantitative data and leave group-based variables behind for a while. For a little while, we're going to sit with quantitative variables, which is going to be variables where we're measuring how much of something does somebody have. So income, reaction times, the number of children you have, how many cups of coffee you drink, how depressed you are, let's say on an index of 1 to 10, how anxious you are, let's say on an index of -3 to +3. Again, higher numbers mean you have more of the variable than lower numbers. And the descriptive statistics we're going to calculate today are going to be most appropriately applied to quantitative variables. And so the three measures of central tendency, which again ask the question, what is a typical score, are going to be our first descriptive statistics we learn about. Now, the three most common measures of central tendency are the arithmetic mean, otherwise known as the average. I bet you're familiar with it. The median and the mode, where the median is the middlemost score directly in the dead center of the number of scores you have, right? Let's say you had 11 people. Well, if you put them in order from smallest to largest, the 1, 2, 3, 4, 5, 6th person would be the median. Whatever score that person has, that score will be the median. Again, more on this in a minute. And then the mode is simply the most frequently occurring or most probable score. And we'll take each of these measures of central tendency in turn. So here is the arithmetic mean. And I've shown it to you here in summation notation, which is that one brand new mathematical concept I wanted you to know. And so let's walk through what this equation shows us. Here we have x bar, which you may recall from our discussion of data, x bar refers to a sample average. And so what I presented you with here is the equation for a sample average. Now, everything to the right of the equal sign is exactly the same. When you're calculating for a population, it's just instead of having x bar there, you have mu, the lowercase Greek letter mu. Right? But how you calculate the average for a population or a sample is exactly the same. Now, most of the time you don't have access to populations, so you're calculating averages for samples. And so you're calculating x bar. So let me translate what this equation is telling you, because I suspect almost everyone already knows how to calculate an average, right? If I have three numbers, let me write on here for you. If I have three numbers, let's say I have 2, 4, and 6. And let's say this is the number of children people have. And so I have 3 people. So n equals 3. because N is a big mama N. I call this big mama N because it's uppercase N. Always stands for how many scores were there, how many people were there. And so I have 3 scores here. N equals 3. And if I was going to calculate the average of these 3 scores, I bet most of us would know how to do that, right? We would take 2 plus 4 plus 6 would be our first step. And that is exactly what the top part of this fraction is telling us to do. It says take all the x's. What are the x's? X sub I. Well, x sub I simply stands for each person's individual response to the question, how many children that you have. And so x stands in for, symbolically, the idea of the variable number of children. X is simply defined as the number of children that you have. And each person, X sub I, has their own unique answer to that question. Many of you probably have 0 children. Some of you may have 1. Some of you may have 2. Some may even have more than that, 3, 4, 5. I don't know. But each person has their own unique X response. Now, I only asked 3 people this question in my current example. And so the first person told me 2. The next person told me 4. And the third person told me 6. And so if I was going to calculate the average number of children for these 3 people, for this sample of 3 people, I would do 2 plus 4 plus 6. 2 plus 4 plus 6. Because that's what this top part of this fraction is telling me to do. Because remember that uppercase Greek letter sigma, which looks like a funny E, all that means is add them up. Take everything over here, everything to the right of that funny looking E, it's not, it's the uppercase Greek letter sigma, and add them up. Where we are always going to be starting at I equals 1, which means start at the first person. Start at the first person, and then go to, boop, N, which means go to the last person. Add up all the people's scores, which I'm sure you already knew how to do when you calculate an average. You add up all the scores. So 2 plus 4 plus 6 is 12. 2 plus 4 plus 6 is 12, but that's only the top part of the equation, right? Down here, that's N. That's the total number of scores, which is what you divide 12 by to get your average. So the average is 4, because 12 divided by 3 is 4, right? And so I share this with you so you can already start to wrap your head around what summation notation means. I also share it with you for another reason, because I want you to notice something about this equation, that there is a sigma in the top, and there's an N in the bottom. And if I was going to draw sorry, repeating myself, a shape around the sigma and the N, I think it makes something that looks sort of kind of like a kidney bean. And so when I look at, in the future, some more complicated equations that maybe look a little scary, and I notice that there is a sigma, that funny looking thing that sort of kind of looks like an E in the top of the fraction, and N in the bottom of the fraction, I know I have an average. And I know how to calculate an average. And so even if there's more going on in the equation then sigma in the top and in the bottom, I know it's got to be a type of average, and so maybe that equation won't be as scary for you. So anytime you sort of see what I call a kidney bean, but whatever, sigma in the top and in the bottom of a fraction, you know you're calculating an average of something. Now, if what you're calculating an average of is just a bunch of scores, well, then you're a bunch of x's, right? My score, your score, her score, his score, right? Then you're calculating the basic arithmetic mean. There'll be other averages in this class, and I just don't want those other equations to look scary to you, right? So I point that out to you now. So, but in this equation, this is the exact same equation whether you're calculating for a sample for x bar or you're calculating for mu of population. The only thing that changes is the symbols that you use. Now, your book likes to use the symbol M for all averages, right? Because that's actually APA style. The American Psychological Association says that you should use M for the sample average. And that's all well and good, but your book doesn't then differentiate between sample averages M and population averages mu. And so I like to use x bar because it's very, very different from mu. And it reminds us that regular Roman letters like x bar refer to sample averages, and funny looking Greek letters like mu refer to population averages. Not to mention, outside of psychology, the symbol of x bar is used by almost all statisticians to denote the sample average. So I want you to know that the sample average is symbolized with x bar, and a population average is symbolized with mu. Now, your book likes to use M for all averages everywhere, but that is a little bit sloppy, and so I'm complicating your life a little bit, right? Got to use x bar for sample averages. You got to use mu for population averages when you're thinking about the exam. When you're my exams that you'll take during week 4, right? Our first exam. When you're taking your quizzes, though, please keep in mind that your book just likes to use M. M to mean the mean, right? Which is just one of the ways that your book glosses over some important, more finer notes in statistical analysis. So, conceptually, though, because again, we can calculate the average, but part of sort of a good broad understanding of statistics is sort of really understanding the concepts that underlie the average. Now, what is the average? The average is the value where the amount of stuff you're measuring balances out above and below the average. It's the number that balances the actual stuff you're measuring. And what do I mean by that? It balances the actual stuff. Well, that means if you have really extreme scores, the average gets pulled towards those extreme scores. You might recall our discussion. Of skewed distributions, right? Skewed distributions have extra scores only on one side when you're looking at the peak and the tails. One of the tails is a lot longer. And one of the reasons why it's called skewed is because the average gets skewed toward those extreme scores only on one side. Because averages are affected by big values. And think about if you've ever been in a class where, everyone got a 70 out of 100, and then 3 people aced the test. Those 3 people are going to make the average closer to themselves than the average would have been to 70, right? Because the average accounts for everybody. The average accounts for every single score, no matter how big it is. And so I like to think of it as like a teeter-totter, where really extreme scores, the average has to move towards them. It actually has to move towards them because it has to balance the actual stuff above and below it, right? Not the number of scores, but the actual values themselves have to be balanced above and below the average. Because let's take a look at my example that I have here. Let's say, again, this is the number of children that people have. Like let's talk about my family. My sister-in-law comes from one of 14 children. I'm not kidding. She comes from one of 14 children. And I'm an only child. And then I have another sister-in-law who has one sister. So she comes from two. And then my other sister-in-law comes from a family of three, right? So if you look at us, I am an only child. Another person has two children in her family. She's one of two. Another is one of three. And then my one extreme sister-in-law comes from one of 14 children. Now, if we were just considering me and two of my sisters-in-laws, 1, 2, and 3, the average would be 2, right? My average would balance out because there would be one above me from 2 to 3 and one below me from 2 to 1, right? 2 would balance the 1, 2s, and 3s perfectly. There'd be the same amount of siblings above and below 2, 1. But the minute you add my other sister-in-law into the mix with her 14 siblings, that average gets dragged towards that 14. Where that 5 now, that new average of 5, is balancing the values below it, 1, 2, and 3, with the one value above it, 14. Because ask yourself this question. How different is 5 from 14? Well, in math, if we want to figure out how different two numbers are, we subtract. So let's go to draw again. So how far away is 5 from 14? And the answer is 9. So 5 is 9 away from 14. Okay, put a little 9 there. Now, ask yourself this question. How far away is 5 from 3? 2. How far away is 5 from 2? 5 minus 3 is 2. 5 minus 2 is 3. Oh. How different is 5 from 1? Well, 5 minus 1 is 4. Oh. So there is the amount of stuff below 5 of 2, 3, and 4. 2, 3, and 4. Well, what is 2 plus 3 plus 4? It's 9. So 5 balances the distance between 5 and the score above it, but also the distance in the actual stuff you're measuring below it, right? It balances the actual values of siblings. 14 was so extreme that the average had to move towards it. That is the idea behind the average. It balances the actual values of whatever you're measuring above and below it. And if you go back to that very first example from my first slide, let's just zoom back there for a minute. The most common score was $2,000 a month, but the average was getting pulled towards these crazy rich people here at the top. Because the average must account for everybody and everybody's actual value. This is different than the median. The median doesn't care about how people's actual scores, not in terms of a let's measure it specifically kind of way. The median simply says, okay, you got a bunch of scores. Rank order them, like let's say in an ordinal fashion, rank order them, and then after you've labeled them from smallest to largest, find the score in the middle score, ignoring the values at this point, just the score that happens to be in the middle. If you have 11 people, it'll be the 6th person. If you have 101 people, it'll be the 50th person, right? Find the score in the middle, And that score is your median, right? Again, only appropriate if you have quantitative data, right? And so let me, but the median isn't getting dragged by super extreme scores, right? It's not getting dragged by super extreme scores because it's sort of kind of ignoring how big the values are other than to put them in rank order. So let's do an example real quick. Let's say this is my data set. Is it going to let me do stuff? Apparently not. Apparently I'm only allowed to draw right now. Okay. Whoops. Am I allowed to edit? Let's tell me why isn't it letting me do stuff? Do just a blank slide then. All right, so let's do a data set. So let's say this is my data set. Let's say this is what's your mood today on a scale of 1 to 10? First person says 10, next person says 2, next person says 4, next person says 7, next person says 1, right? Now, if I want to figure out the median, the very first thing I have to do is put these people in order. So I've got 1, 2, 4, 7, and 10. Well, now I have them in order. And I simply, I dropped my pen, hold on. I simply find the score in the middle. It does, right? This would be the median because it's the score in the middle because there's 2 actual scores above it and 2 scores below it. And 4 would be the median even if, instead of having a 10 here, this number was 100. Let's say a person, I say on a scale of 1 to 10, what's your mood today? And one person's like, 100. 4 is still the median because 4 doesn't care about how big the numbers are. All it cares about is putting them in order and finding the score in the middle score. And if you have an odd number of numbers, right? You never have a data set of 1. 3 numbers, 5 numbers, 7 numbers, 9 numbers. An odd number, it literally is the number in the middle with the exact same number of scores above and below it, right? If on the other hand you have an even number of numbers, 2, 4, 6, 8, 10, 12, 102, 104. So I'm going to give you an example of that. Let's say you have 10, 100, 2, 5, 7, and 9. Now I have an even number of numbers because I have 6 numbers, right? N equals 6 now. So the number of numbers I have is 6. So first thing I'm going to do is put them in order. 2, 5, 7, 9, 10, and 100. I find the middle 2 numbers and I simply average them. So the average of 7 and 9 is 7 plus 9 divided by 2 because I'm getting the average of 7 and 9. 7 plus 9 is 16. 16 divided by 2 is 8. So in this case, the median is 8. Right? Median. The mode, on the other hand, is either, if you have discrete data, you remember discrete versus continuous? If discrete data, it's the most frequently occurring score, the one that shows up the most often. Now, if you have truly continuous data, well, let's say every single score is unique, right? Let's say you're talking about like reaction times, and every single reaction time is totally unique because you have very precise measurement. The mode is going to still exist. It's simply the most probable score, right? If you have discrete data, let me give you an example of discrete data. Let's say this is my data. 1, 2, 2, 2, 7, 9, 9, 10. Well, the mode in this case is 2. Because 2 shows up 3 times, and all the other numbers either show up twice or only once. That's discrete data, right? Where there's a limited number of possible choices. You're not cutting things in half. Can't cut things in half, right? I don't have 2.5 in here. But if you have continuous data, in order to figure out the mode, you're going to have to look at a density plot. Remember density plots? Where you have your scores along the x-axis, and you have how probable those scores are along the y-axis. Remember, the x-axis is horizontal, the y-axis is vertical. Well, here I can identify what the mode is because I find the peak. I find the number that is the most probable. Over here, along the y-axis, we have how probable a score is. Down here, we have the actual scores themselves. And here I have a variable, the number of hours World of Warcraft players spend online. And let's say the bottommost value is like 5 hours. Then you have 6 hours, 7, 8, 9, 10, 11, 12, all the way to 14 hours. And I am able to identify the mode as 6 hours. That is the mode because it's the most probable number of hours. Even if I measured things really specifically, 6.1 hours, 6.2 hours, 6.3 hours, I'm able to identify 6 as the modal response, the most common response. We call that the modal response, the most common. The most common or the most probable. And that's the idea behind the mode. And so for a single variable, you have 3 different ways of answering the question, who is typical? You have the mean, what number balances the actual stuff, gets dragged around by how big the scores are. You have the median, which is literally the center of the data, the exact same number of scores above and below it. And you have the mode, the most frequently occurring or the most probable score. And sometimes you have 3 different numbers, and sometimes in a variable, the mean, median, and mode are the same. Just depends on your variable. But measures of central tendency, mean, median, and mode. And one is not better than the other, right? Now that we've sort of wrapped our head around what the mean, median, and mode are, conceptually, how to calculate them, how to find them, it should be clear, I want to make clear that one is not better than the other. They just sort of address different aspects of answering the question, who is typical, right? So I want to go over sort of the pluses and minuses of the mean, median, and mode. And I definitely see knowing these sort of pluses and minuses, these pros and cons, these good things and bad things, I see those in your future. I definitely see being able to calculate mean, median, and mode. I definitely see their definitions in your future, but also their pros and cons. So let's go over them. The 3 M's, mean, median, and mode, the good and the bad. The mean is the most common. It is the most common descriptive statistic. It's the one people always want to know. Students come up to me and they don't go, what was the mode exam score? No. What was the median exam score? No. Students always want to know what the average was. What was the average exam grade? What was the arithmetic mean? That is a good thing. It is also used in inferential statistics. You know those statistics will eventually calculate where we're going to ask and answer cool research questions like, is age related to cognitive functioning? The mean is used to answer those questions. And the reason the mean is used to ask and answer inferential questions is because there's no loss of information. Every single person's actual value for the variables you're looking at are addressed. You're collecting information and then calculate a number that summarizes everyone's actual scores. So it uses every single data point's actual values, which is a really good thing. And so it actually balances the values of the stuff you're measuring. If you care about the specific number of children people have, the mean is going to summarize everybody's score and balances the stuff above and below it. That's a good thing. But because it pays attention and incorporates everyone's actual values, scores that are weird, that we call outliers, scores that are really far away from everybody else, have a big impact on the average. So we say that the average is not tough. It's not robust. It's highly affected by these extreme scores, right? Highly affected by those outliers. And remember that first slide, that one person with a monthly income of $45,000 was having a big effect on the average, right? And so that's sort of a drawback of the average. Because it incorporates everybody's actual score, that's a good thing, no loss of information, but that has drawbacks because extreme scores called outliers are going to greatly affect it. So it's not robust. It's not tough. It's not immune to outliers. Now the median has some good things about it too. One of the good things about the median is that it is robust to outliers, right? I gave you that example where it didn't matter if the top score was 10 or 100, the median was still 4. It didn't matter, right? So the median is robust to outliers. Another good thing about it is it's the literal central center of the data. If you're going to call it a measure of central tendency, well, it's a good thing that we have a measure of central tendency that is literally in the center. Same number of scores are above and below it. If you have 11 scores, it's the 6th score. If you have 101 scores, it's the 50th score. It is literally the center of the data. The downside of the median is it's not used in what are called parametric inferential statistics. And parametric is just a fancy word to mean the average. And you can't substitute the median when you're dealing with those cool inferential statistics we're eventually going to calculate to ask and answer research questions. You can't use the median because those equations call for the mean. You need to have the mean. And so that's kind of a drag. If I want to answer cool research questions like is age related to cognitive functioning or is gender related to aggression, I can't use the median. I have to use the mean. So that's a bummer. Another downside of the median is it actually ignores the data. Except to put people in rank order and finding that central value. If the top score is 10, if the top score is 100, the median doesn't care. Well, maybe it's meaningful and important to keep track of the actual values of the score. So there is a loss of information. So the good things about the median is that, well, it's robust to outliers. Outliers aren't going to affect it, but maybe the outliers matter, right? And so that's going to be a drawback of the median. And again, one measure of central tendency isn't better or worse than another. They simply ask different questions about the variable. They get at different things. And oftentimes in research, you'll have researchers reporting all three, mean, median, and mode. And you just need to know the pluses and minuses of all three. And the mode has good things and bad things too. The good thing about the mode, in the discrete case, where there's a limited number of possible outcomes, right? So like, let's say the number of children you have is discrete. The modal response will actually occur in the data. And if you want to say who's typical, having a value, the mode, that represents a score that actually occurs in the data is a good thing because the median might not occur. You remember when we were averaging 7 and 9 to get a median of 8? That wasn't actually a score in the data. Or if you're calculating an average, remember how we had a data set of 1, 2, 3, and 14, and the average was 5? Well, in both those cases, we were reporting a number, 8 and 5, right, for those particular examples, that didn't actually occur in the data set. Well, with the mode, it is usually a number that actually occurs because it's the most frequently occurring score. Now, in the continuous case, where you have an infinite number of possible outcomes and every single person has their own unique score, the nice thing about the mode is that the slope of the density plot is 0. Now, this is really only interesting if you're a math type person like me. So you're not going to be tested on that. You do need to know that in the discrete case, the mode is a number that actually occurs in the data. But in the continuous case, go back to our lecture on data, discrete versus continuous, limited number of possible choices, can't cut it in half, 1 child, 2 childs, 3 children, 4 children, versus continuous, an infinite number of possible reaction times. In the continuous case, if you have a density plot where the scores are down here, from small to big, let's say it's from 1 to 100, right? And you have how probabilistic they are up here, right? For those math geeks like me, that the place on this probability plot, that is the mode, the slope of that is 0. This has a slope of 0, this straight line. And that's only interesting if you're a math geek like me. But I shared that with you for the math geeks among you. For the rest of you who are like, oh my God, the slope of the density plot has 0 where the mode is? What is that? You do need to know that the good thing about the mode in the discrete case is that it's a number that will actually occur in the data, right? Let's give you the discrete case again. 1, 2, 2, 2, 5, 9, 10. Ah, here's the mode. And look, the mode is 2. It actually occurs in the data, right? This other thing for the continuous case is interesting for me. But there are drawbacks to the mode. Good thing is that will usually occur within the data set. It will always occur in the data set in the discrete case. We're talking about a limited number of possible outcomes. But the bad thing is it ignores all the other data. Literally, anything that's not the mode doesn't care about. Well, that's kind of a drag. It ignores all the other data. That's lame. Other bad things about the mode is that it's often what's called biased. Now, that doesn't mean that the mode is prejudiced against other measures of central tendency. No, what bias means in this case, is that oftentimes sample modes don't look like population modes. And that's what bias means in the world of statistics, that our samples don't look like our populations. And if we want our samples to look like our populations, that's a bit of a problem, right? And of course, another drawback of the mode is just like the median, you can't use it in those cool inferential statistics that require the mean, right? Can't use it. Can't use it to answer cool research questions, like is age related to cognitive functioning? Now, at this point, I want to sort of combine our discussion from distributions with our discussion of central tendency, right? So let's dust off our brain and remember our discussion of distributions. And we learned about the normal distribution. Now, a normal distribution is defined as a distribution with a single peak, where as you get scores above that peak and scores below that peak, they become less and less likely. Again, scores are down here along the x-axis. In this case, it ranges from +3 to -3. And how probable those scores are along the y-axis, right? And a normal distribution, a Gaussian distribution, is defined as any variable that has sort of one very, very common score, and as you get above that score or below that score, scores get less likely. Well, let's combine that knowledge of a normal distribution with our knowledge of the mean, median, the mode. On a normal distribution, the mean, median, and mode are all in the dead center. And in fact, they're all exactly the same. And you can sort of eyeball it. The same number of people are going to be above and below this peak because the average here is at 0. Not only is the average at 0, but the median will be at 0 and the mode will be at 0. Now, on this particular example, and on any normal distribution, let me draw you a different one. Let's say I have another normal distribution. Let's say this is a normal distribution of reaction time, let's say it's IQ. I like IQ as a variable, right? And let's say the middle value is 100. Well, that means the average will be 100. Woo. X bar equals 100. Woohoo! The median will be 100. And the mode will be 100. On any bell-shaped curve, the mean, median, and mode are all going to be in the center, and the exact same number. And that is one of the beauties of a normal distribution, is that the mean, median, and mode are all at the same place. And so our three different ways of asking the question, who is typical, are all in perfect agreement. Who is typical for IQ? Well, the average IQ, arithmetic mean, is 100. The same amount of IQ will be above and below it. The center value, the same number of people, will be above and below a score of 100. And the most common, the most probable score for IQ is 100. So in any bell-shaped normal distribution, the mean, median, and mode are exactly the same. So here I have, again, that I have done a pretty picture for you. Here I have a histogram with the density plot overlaid on top of it. And this is in fact what the distribution of IQ looks like in the population. IQ, cognitive ability, is a normally distributed Gaussian distribution, right? Where not only is the average 100, but the median is 100 and the mode is 100 as well. This is the most probable score. It's the score in the dead center, median, as well as if I calculated the average, I added up all these scores, and I added up all these scores, and I divided by the total number of scores, n, big mama n, I would again arrive at 100. That's the beauty of a normal distribution. The mean, median, and mode are all at the same place. And in fact, any symmetrical distribution where the left side of the graph and the right side of the graph are roughly the same, the median and the mean are going to be in the same spot. They're going to be in the middle. Symmetry means the left and right are the same. That's true in faces. Left side of my face and the right hand side of my face might be symmetrical. But that's true in graphs as well. Symmetry, symmetrical. The left and right sides are the same, right? So here I have a uniform distribution, right? And if I draw a line down the center, this graph is roughly symmetrical. Now, it's not perfectly symmetrical because nature is messy, but it's roughly symmetrical. And so both the mean and the median would again be at 100, because that's what that number is hiding underneath there. Right? In this symmetrical distribution, the mean and the median are both at 100. Right? Now, the mode here, you can actually identify it. This does have a different mode because life is messy, right? That's the modal response. But if this was a perfectly uniform distribution where all the bars were exactly the same height, you would actually say this is non-modal. It's just there is no modal response here. No mode, because every single score is its own, is just as likely as any other. So there's no mode. There's no most common score. But on any symmetrical distribution where the left and right hand side of the graph are roughly the same, the median and the mean are going to be in the center, just as they are in a normal distribution. Now, this is my bimodal distribution. Now, in a bimodal distribution, just like a bicycle has two wheels, a bimodal distribution has two modes. It has two scores that are the most common. In this case, I have a mode at 2, and I have a mode at 4.5. Two modes. Now, this graph is roughly symmetrical. The left and right-hand sides of this graph, are roughly symmetrical. And so once again, to find the mean and the median, I would draw a line down the middle and go, looks like the average and the median are both somewhere between 3 and 3.5. Because on any symmetrical graph, the mean and the median will be roughly in the center. And then in a bimodal distribution, you have two modes. Now, the last type of distribution we went over was skewed distributions. And so ask yourself this question. Think about it. Now, what is skew? Skew is when you have something with a single peak but then one tail is a whole lot longer than the other. Now, this is a density plot. So again, we have scores down here, and we have how probabilistically scores occur along the y-axis. That's terrible. Just going to label this P for probability. So the actual scores are down here along the bottom, and then how probable a score is along the y-axis, right? And so if I actually wrote in the numbers here, so let's do that. So let's say this is 1, 2, 3, 4, 5. Because let's say this is the number of children people have, right? There's going to be a hard stop at 0 with some outliers over here at like 14 and, you know, 20, however many counting that show all the way over here, right? There is a most probable score, right? And that most probable score is going to be here. But what would the average be? Now, again, I just made up this example, and I picked any numbers. These are not the accurate numbers out there in the world. But bear with me, right? Just bear with me for a little bit, right? I have, you know, I've been able to identify the peak of the mountain. The most probable score is the median. Excuse me, the mode. Sorry, scratch that. The most probable score is the mode, right? And I've been able to identify it here as the peak of the mountain. Now, is the median going to be affected? Let's say I start dropping extra extreme scores here. I start adding people to my data set. I add a person with 20 kids to my data set. I add a person with 22 kids to my data set. I add Solomon to my data set with all 600 children that he supposedly had, or right? I start adding outliers. Is the average going to be affected? If so, how much? Is it going to get dragged off the top of this mountain? Is the median going to be affected if I'm adding scores only on one side? If the median will be affected, how much? Wrap your head around that for just a minute, and then I'll tell you the answer. And so let's look at these other two data sets from last time, the examples I gave you for skew. Here we have something with positive skew on the top, right? Well, the most common score is going to be unaffected by this skew, right? It doesn't matter how many extreme scores are over here. The mode doesn't care. So the mode is going to be here. Sorry. Sorry, I'm dealing with my slide for a minute. Bear with me for a second. All right. Right? The mode doesn't care that there are outliers, right? The mode doesn't care that there are outliers. This line right here, is going to be the mode. It doesn't care that there are outliers over here. The top of the mountain is always the top of the mountain. The peak is always going to be the mode. But as you add extra scores, right? If I add a 26 here, because my score here is 25, right, up here. If I add a 26, if I add a 27, if I have a 28, the median's going to have to move over 1 for every extra outlier I have on one side. Because although the median is relatively immune to outliers, it's affected a little bit. The mode is completely unaffected by outliers. The median is affected a little bit by outliers. So this is going to be the median. And then over here towards the outliers is going to be the mean, because the mean is affected by skew, because what it causes skew, outliers, and the mean is heavily influenced by these extreme people over here only on a single side. So to recap, we have we have this is the mode on a skew distribution, followed by the median, because the median has to move over 1 for every extra extreme score, only in the positive side, and this is going to be the mean. Now, if you have negative skew, it's just the reverse. In negative skew, left-hand skew, where there are extra extreme scores, is on the left-hand side. And so everything is just reversed. Once again, the peak of the mountain is where the mode is, always. But because there are extra extreme scores on this left side, the median moves over 1 for every extra extreme score, because the median is robust to outliers, but not completely unaffected by outliers. It's a little bit affected by skew. And this last one is going to be the mean. It's going to get pulled into the direction of the skew. Because remember, the direction of the skew is where the tail is longer. Up here on the top is positive skew. Up here on the bottom is negative skew. And the average gets pulled in the direction of the skew. Wherever the tail points, that's the direction of the skew. So where the tail is where the average is. Where the peak is where the mode is. Because the mode is unaffected by skew. Top of the mountain is always the top of the mountain. The median is a little bit affected by skew, but robust to outliers, so it doesn't get dragged very much towards the skew, where the mean is going to get pulled a lot towards the skew. I see a graph like this in your future, where you'll have to label the mean, median, and mode on a graph like this, a skew distribution. And so I strongly recommend you sort of wrap your head around this idea. And this is where I'm actually going to stop this video. And I'll make a separate video where I sort of broach variability. Instead of having one giant hour and 50-minute long video, I'll split them up into 2 smaller videos. And so I'll end the video here, but there is another video entitled Variability. And if you want to go watch it now, feel free. Or you can sort of stop here and wrap your head around central tendency before watching my variability video. See you next time.